think harder because once it's taking too late. Yeah. Was this a wow? Yeah, because I had to help the program. Yeah.
That's very bad.
Can we just go ahead and continue and ask questions?
Check your distance.
Actually, this is good. I think the screen. You can see your slides better,
Wait,
now, right?
there's still like backlight.
Huh?
I don't know, there's still like the top light.
But our city is involved in
Like near the
Washington,
front.
but we're not in the city. Yes.
Nope, that's bad. I think they should do a light of the right board versus the left board. See that's exactly what I did.
Oh, yes.
Woo! Wait, people actually want this? I feel like that's not a good solution. Wait, does anyone actually want it all dark?
Raise your hands.
Okay, I'm so sorry to do this, but who wants it not dark? Okay, so unfortunately, I will go with only unanimous decisions here, so we're not gonna have it all dark, just because it makes it impossible for some people to focus.
Yeah.
This is slightly better, I think.
Wait, is this the minimum?
Well, I don't know how to turn off those lights up there, is the one thing.
I think you can, I just don't know.
They have a bunch of set presets. I'm not sure how to work with it. I'll figure it out with the next meeting.
You know what, we'll figure it out next time. And for now, this is better.
Okay, awesome. So today we're going to be talking about the introduction to machine learning. This should just be covering the basics if you guys want to kind of get into it and start making your own machine learning models. And for the homework for this week, we'll have you guys working in a Colab template that's on our website, and you guys will get some experience working with that. And as always, if you guys have any questions, feel free to message your TAs or message us on Discord, and we can help you out. So first off, who here has heard of machine learning? Raise your hands. Yay! Some of the people who were here earlier, I told them about the questions, so they had a head start on thinking about the response. But what have you guys heard about machine learning? Hands up. Yes.
It's related to AI or software.
Related to AI? Okay.
Uses some sort of neural networks?
Yeah, neural networks? Okay, that's really good actually. Yeah, neural networks are a cool concept. Any other things? Yes?
Test something, get it wrong, change stuff, try again.
Yeah, that's a good model to follow, I feel like. Just keep on trying different types of things and just seeing how your accuracy changes with different models. That's a good approach. Any other thoughts on machine learning? Okay, awesome. So yeah, what is machine learning? So we can begin by understanding what machine learning actually is. So at its core, machine learning involves teaching machines to understand and recognize patterns in data by allowing them to make decisions or predictions without being explicitly programmed. Fundamentally, it's about helping machines interpret and act on semantic information, similar to how humans recognize patterns. So you might wonder if machine learning is just applied statistics. There is an overlap, but the main difference lies in that lies in who's doing the analyzing. So in statistics, humans are analyzing their own data, but in machine learning, you're feeding a version of the data into the machine, so the machine can do the analyzing for you. And they learn from the data that we feed them. So the process typically follows this flow. So you provide the data to the machine learning model, and the machine builds a model from that data, and then we optimize that model to improve the performance. But it's important to note that the machine learning is data-driven, so that means that the machine can only make insights based on the data that you give the machine. So the quality of the data that you give your machine is super crucial, because if you give your machine maybe some skewed data or some skewed data sample, then the outputs of your machine learning model will be skewed as well. And we'll talk about this more in the AI ethics unit, which is week 7. But yeah. So first off, I have 2 objects on the screen here. Can anyone tell me what the difference is between these 2 objects? Hey guys, you guys are all college students. Okay, yes?
One has green color and one has red color.
Awesome, yes.
I was gonna say color.
Color, okay. Yeah, that's a good first difference. Are there any other differences? Yes?
I think they look the same.
Color? Or you think they look the same?
Yeah.
To a machine, if you don't give it any data, it might think it looks the same.
One of them is living, one of them isn't.
Yeah, okay, that's really good. One is a living object, one isn't. Yes?
One has wheels.
One has wheels. Awesome.
One big, one small.
One big, one small. Okay, yeah.
I mean, one can like travel around significant areas, but one is kind of more stationary.
Yeah, one has mobility, one doesn't. There was one hand back here. Yeah.
One tool, one not used by.
Oh, okay. Yeah, awesome. One is a tool and then used by humans and one isn't. Are there any other hands in the back? Prove to me you're not just on your computers. Just kidding. Yes.
One is more like horizontal and the tree is more of a vertical image.
Yeah, awesome. Yeah, so these are all like factors that we use to tell the differences, right? So if we're looking at how we can make a machine learning model tell the difference between these two objects, how do you guys think that the machine learning model could use these features to differentiate between these two objects? Any ideas? It's pretty much what you guys were saying before. Does anyone think that they would use those features to tell the differences? Whoa. Okay, everyone's hand should be up. Yeah. But yeah, they will use those features to tell the differences. So basically, one example of this is by looking at the characteristics and variables of the two objects that you're trying to tell the difference of. Because in this example, if we're looking at the bike and the tree, right, we can say that, hey, one of them has leaves and one of them has wheels, which I think was mentioned. And we can have that be our basic data set that we feed into the machine learning model that, hey, if we have these two objects and we're giving you these two characteristics to analyze, tell me if you can categorize which one is a bike and which one is a tree. And a machine can't really read the words no and yes like the way a human can. So for a machine, we would feed it numbers. So in this case, what is 1 and 0 standing for? Hand. Yes.
Boolean.
Boolean. And then you hand up here.
I was just gonna say yes or no.
Yes or no. Okay, awesome. Yes, it's a Boolean. That's yes or no. So perfect. So in this case, what we're doing is we're feeding it a binary representation, which binary just means zeros and ones, of whether it has leaves or has wheels. And we're going to feed those numbers into the machine because the machine can use those numbers to be able to analyze whether it is a bike or it is a tree. So, yeah. So, for example, one example of a machine learning model we can use to tell this difference is called SVMs. So the way that we can use SVMs, which stands for support vector machines, is for classification or regression. So in this graph, you can see that we first plotted the data, and then we used it to train our model that can help distinguish between the different classes. And in this case, the two classes are the bike and the tree. And then we plot our data on this graph. And this is a crucial step because visualizing this data allows us to understand the relationships between variables and see if these classes are easily separable. On the graph shown here, we have two features on the axis. One is, if I zoom in, whether it has leaves, and then one is whether it has leaves, or one is whether it has wheels. So this visualization gives us a sense of how the machine will differentiate between whether something is a tree or a bike. And then also, next we introduce a line separator. So this is a line that separates the two classes. And based on which side of the line that they fall, this is where the machine learning model will categorize that object. So you guys can see that so you can see that like they'll plot a line in a machine learning model between all the points of where it thinks it's a bike or it's a tree. And that line is that like middle like black line. And based on whether the points are below that line or above that line, changes the classification of whether the machine learning model thinks it's a tree or it's a bike. So this middle line is called a hyperplane. What a hyperplane is it's a subspace that is one dimension less than the space it's in. So for example, if we're working with 2 dimensions, which a graph is 2 dimensions, then our hyperplane would be modeled as just a line. But if you're working in 3 dimensions, then our hyperplane would be a 2D object or a plane. So in this case, the hyperplane is what separates our different classes between our bike predictions and our tree predictions. And the next concept that you guys should know for support vector machines, which is this machine learning model, is support vectors. So support vectors are the data points that are the closest to the hyperplane, and these play a crucial role in understanding and determining the position and the orientation of the hyperplane. Without these support vectors, the decision boundary would look very different. In the graph, the support vectors are shown as the points lying closest to the hyperplane on either side. Another important concept to understand is the margin. This refers to the difference between the hyperplane and the nearest data points from each class, which are our support vectors. So the support vectors, just to reiterate, are a vector, which is basically like a line with an arrow between the closest points to the hyperplane to that hyperplane. So in this case, the margin is critical because it's what SVMs aim to maximize. The larger the model, the better that the model is able to generalize to its new data. Essentially, a larger margin reduces the risk of misclassifying future data points since the decision boundary is even more robust. In the illustration, the margin in the space is in between the dashed lines, which represents the data in the two classes. So to summarize, the hyperplane is our decision boundary, support vectors are the closest data points to that hyperplane, and the margin is the difference between the hyperplane and those support vectors, and the goal of SVMs is to maximize that margin, ensuring a more reliable model. So this combo of minimizing margin and carefully selecting support vectors makes support vector machines extremely powerful for classification tasks. And classification tasks are when we're trying to classify something into groups. So in this case, it's classifying it into whether it's a bike or it's a tree. And the key takeaway here is that SVMs is all about finding that optimal boundary between classes that generalizes well to new unseen data. So yeah, so in this note, the best hyperplane is the plane that has the maximum distance from both classes, because this means that there's less confusion about points that are really close to the hyperplane that could be either a bike or be a tree in this example. And in terms of the model output, let's say that we put in our values for zeros and ones for has leaves and has wheels, and then we get this output, and this output is telling us whether or not the model thinks it's a bicycle. And if the model is telling us there's a 0.75% chance that it is a bicycle based on the data, and a 0.25% chance that it has wheels based on that data, that means that the model's pretty good. It has a 75% accuracy, because if it has the correct data, it's guessing the correct thing 75% of the time. But we can make this model better, right? Because basically what we're seeing is that if it has leaves, it is only correctly predicting that it is not a bike 75% of the time. So how can we make this model better? Are there any ideas for how we can make machine learning models better? Yeah, okay, let's do this.
More data.
More data, awesome.
Teaching it.
Teaching it,
Mine sort of already said.
more data, okay. And then, did you have a hand?
Same here, more data.
Same, yeah.
Maybe a nonlinear line would better fit the data.
Awesome, nonlinear line,
Feedback loop.
feedback loop, okay, yes.
Using more parameters.
Using more parameters, awesome, yeah, so those are really good suggestions. If we don't have a linear line, then we could even go into something called logistic regression, which is when you have not just one line plotting it, but you would have more of a curve. And a feedback loop would let you make iterations of this model, so you could have multiple models training on the same data, and over time those models would learn from each other. So yeah, those are all great suggestions. So I think one of the things is adding more features, right? Adding more data. So in this example, right now we just started with has leaves, has wheels, but maybe the model has trouble finding those features, or it's not really that many features for the model to train on. So some good features to add, which people mentioned earlier, was height, mobility. Some other ones I added was, does it have a smooth texture like a bike, or does it have a rough texture like a tree? Does it have metal? Does it change seasonally? And in these cases, all of these are being represented by zeros and ones, which represent no's and yeses. And to make our data even better, we could even have classes that aren't just the bicycle and the tree. We could add thing 3, thing 4, thing 5, right? And these could be different objects. It could be an animal, or it could be a car. But these could be more objects for it to be able to classify this correctly, because this is right now training on a bike or a tree, right? But let's say I throw in a car. It might think the car is a bike because it's a smooth object, it has wheels, So in this case, if we add more data or things, it includes a variety of different things that our machine learning model can use to recognize the different patterns between horses and chairs. So by giving our ML bot a wider understanding of what makes a tree or what makes a bicycle, by feeding it a sufficient amount of data, each with its own unique and diverse characteristics, we can help the model also bypass any potential edge cases or exceptions. So an edge case is basically if there's a picture given to it that it isn't expecting, it learns how to deal with that edge case better. So the next thing that we're going to talk about is PCA, or principal component analysis. So principal component analysis is a machine learning technique that is used for dimensionality reduction. So let's break down what that means and how PCA works. So why use PCA in the first place? So imagine you have a data set with many features or variables, things like measurements, observations, or signals. When the number of these features becomes large, the data can become difficult to manage or analyze. This is referred to as the curse of dimensionality. Too many variables can make it hard for a model to find patterns, leading to a lot of what's called like noisiness in the model and slower computation, and this also lessens accuracy. So if we walk through the steps of PCA. So the first step of PCA is to center the data. So by subtracting the mean of each variable, which mean just means average, this shifts the data so that it's centered around the origin. This is important because it ensures that PCA looks at the variance within the data rather than focusing on overall values. The next thing that's important to look at is covariance matrix. We calculate the covariance matrix, which the matrix tells us how the variables relate to each other, whether they tend to increase or decrease together. Strong relationships increase redundancy, meaning that we can combine these variables without losing too much information. The next important concept is eigenvalues or eigenvectors. This is also like a linear algebra concept, but basically the PCA decomposes the covariance matrix into eigenvalues and eigenvectors. Eigenvectors show the direction of maximum variance in the data, while eigenvalues tell us how much of the total variance is explained by each eigenvector. The principal components are then ranked by the size of their eigenvalues. So the first principal component explains the most variance, and the second explains the next most variance. So basically, if you have a lot of variance in your data set, principal component analysis is good to help reduce that variance in your data set to help the machine learning model make its predictions. And the final thing is transformation to a new space. So we use these eigenvectors to transform our original data into a new space which is defined by the principal components. So this means that we project our data along these new axes, which reduces the number of dimensions while still keeping the most important information. So why is this important? By keeping only the top principal components with the highest eigenvalues, we can dramatically simplify the data set. For example, if you have 10 variables in your data set, right? Like we had 10 things that we were looking at in our old data set, your principal component analysis might tell you that there's only 2 or 3 of those variables that are making the most positive difference, and it's possible that some of the variables might be actually making your machine learning model worse. So by doing principal component analysis, you can see which one of your variables is impacting your model positively the best, which allows you to work with fewer dimensions, which might have a more meaningful impact. So if you guys go into like data analysis and stuff like that, this is super useful because it's not always the case that more variables is better, because you could have a variable that is skewing or confusing your machine learning model, so it's good to cut those out. So benefits of PCA is that it reduces complexity because it eliminates any redundant features that you don't need. It speeds up computation because with fewer dimensions, these models can run faster. And it handles noise because by focusing on variance and by naturally filtering out all this less useful information, we don't have as big of like a diversified data set if you look at like it graphically, because it's easier to find patterns. So if you look at this image on the slide, you can see how PCA works visually. The leftmost graph shows our original data with no principal components applied. As we move to the right, you can see how the eigenvectors, which is the directions of maximum variance, are calculated. These eigenvectors become our new principal components. As we move to the right again, you can see how eigenvectors, which is the direction of maximum variance, is calculated, and these become our new principal components. The final plot on the right shows us how the data has been projected along with these new components, highlighting the key areas where the data varies most. So to sum it up, PCA is a super powerful tool. It helps you simplify your data, retain the most important features. You guys should definitely be using it, and you guys will get to read about it more in the homework as well this week. And the next thing I think is super important is train test splits. So when you guys start making your machine learning models, you'll have a bunch of data, right? But if you train your model on all this data, or maybe I should ask you, do you guys see any issues that could come up if you train your model using all your data? Yes?
One thing that could happen is your model is too accustomed to only your data, so anything outside your data it's not really accustomed to, it can't really detect properly.
Yeah, awesome. So that's basically called overfitting, which is when your model is like super used to the data it's working with, so it can't notice anything outside of it. Yes?
If you put in too much data, then you are like kind of susceptible to like you're more likely to like grab like some inadvertently grab some bad data.
You could grab some like bad data. That makes sense. And then these two.
If you train with all your data and you're testing data with that it's already trained on, you're not getting a very good indicator of how good your model actually is.
Okay, awesome. Yeah. Okay. Twinning. Yeah. Any other theories about it? Okay, that's awesome. Like 4 responses. No, just kidding. But yeah, train test splits. So basically, the big thing about data splitting is that we want to have a ratio between our training set and our validation set and test set, which I'll define what those are later. But basically this makes sure that our model can generalize well to new data, and it isn't just memorizing the data that we give it. So first, if we're talking about data splitting, we take the majority of our data, usually around 70%, and we use this 70% for our training set. So with the training set, this is the data that our model will learn from. It will look for patterns, relationships, patterns, and it'll use these trends to optimize its parameters, which are the internal settings that a model uses during its training. And then after that, we have the validation set. So this is a smaller subset of the data, and it serves a very specific purpose. After training the model, we use this set to tune the model's hyperparameters. This is a term that I've thrown around, but I would put this in your guys' notes. Hyperparameters are settings that we choose before training the model, and these include things like the learning rate of the model, which is how fast the model learns, or the complexity of the model, or the number of layers or nodes, which I know you're talking about neural network. But neural network is basically, it's kind of similar to the human brain. We'll talk about it later. But all these types of things are tuned by hyperparameters, right? So importantly, the model has not seen the validation set while it's training. So this gives us a good sense of how much the model is generalizing without overfitting. So what's overfitting? Overfitting is a very common issue in machine learning, which is when a model performs very well on the training data, which as I said is 70% of the data set, but it performs very poorly on the new data. And this is because it has overtrained itself on the data that it already has, where it can't adapt itself well to new data, so that kind of makes our model useless, right? Because it has good accuracy, but we can't apply to anything else, so it's not super useful. So that's why we want to have our test set at the end, which is completely separate, and we never touch the test set while we're training our model or testing our model until the very end. And then once we have trained and fine-tuned our machine learning model, then we use the test set for the final evaluation to see if our machine learning model actually works properly. And this is our unseen data, so it's the best measurement of true performance in the real world. And in research, for example, a lot of times people will leave 10% of the data set and never touch it until the final stages, just to make sure that they're not overfitting their data. So yeah, a common ratio for the split is 70-30, 70% for the training set and the remaining 30% for the validation and test sets. You could do 80-20 or something like that, but then that's more suspicious because it's you only have 20% to test with. So yeah, I think 70-30 is what I'd recommend, but it can vary depending on what you're looking to do. But yeah, the principle remains the same. We want a large enough training set to build a robust model and separate validation and test sets to ensure that the model generalizes well. So to summarize, the training set is used to learn the patterns in the data. The validation set is used for tuning hyperparameters and preventing overfitting. And the test set is used for the final evaluation to gauge how well the model will perform on unseen data. This data splitting process ensures that the model can both learn properly and also perform properly. So here's a good graph, I think, that kind of demonstrates underfitting, balanced overfitting. So underfitting is when our model just flat out does not work that well. You can see that it has a straight line and it's not really modeling the shape of the curve. So in this case, if we did use this model to make our predictions, I don't think I must string up there. But you can see that a lot of the points are really off the line, right? So if we make a prediction with this, we could have a lot of inaccurate results. Basically, the blue line is our prediction, if we're looking at it like that. And then a balanced line, this is kind of what we're looking for. We want something that is generally kind of following the pattern or the shape of our data, but it isn't too overfitted where it means that it's not actually working properly, it's just kind of putting it up there. And then overfitting is this is way too accurate, right? Because it's perfectly working with the data that we have. And if we have a new point that's thrown in there, there's a good chance that our overfit model will not work on that new data. So I think this is a good kind of evaluation. And then one thing that I think is really good to know is confusion matrices. So that's the graph that's on your guys' left, I think, just me. But yeah, basically a confusion matrix is, it has true positives and true negatives and false positives, false negatives. Basically what this means is that if you are classifying your data, you have, for example, I think this has migraines, doesn't have migraines, and then the predictions of whether the model predicts if it has a migraine or doesn't have a migraine. So a true positive is when the person does have a migraine and the model does predict it correctly. A false positive is when the person doesn't have a migraine, but the model thinks that they do have a migraine, so it's falsely positive. A false negative is if the person has a migraine, but the model thinks that they don't have a migraine. And then a true negative is if that person doesn't have a migraine and the model also thinks that it doesn't. So basically, what we're looking for is the orange here, is we want our true positives and we want our true negatives. And confusion matrices are really good to plot in machine learning because a lot of times your model might learn from your data and just lump everything in one set, and I'll explain that later, but that'll lead to a lot of false positives and false negatives. So one really good example of this is the COVID-19 pandemic, right? Because, for example, probably only like, I'm making up a number here, but like, let's say you have a population and only like 2% of them have COVID, right? Because usually it's not like 100% of the population has COVID in any given sample set, it's like only 2%, right? And if we throw that at our machine learning model, our machine learning model could easily say that, hey, all of these people have COVID, or all these people don't have COVID, sorry. And then that'll automatically get this machine learning model 98% accuracy, which sounds pretty good, right? Because 98% of the people don't have COVID. The machine learning model figures that out and just says, hey, everyone doesn't have COVID. And then boom, you have like a 98% accuracy rate, but your model isn't doing anything because it's just saying that everyone doesn't have COVID off the bat. So that's why it's so important to look at these false positives and false negatives, because then we can see that, hey, there's a ton of, there's a ton of false positives, I think is what it would, false negatives. So this shows us that the model doesn't actually work that properly. So we should actually maybe change our data, or we should like edit it so that way we have maybe like 50% of people who have COVID, 50% of people who don't have COVID, and make our model train using those things. So it's not just lumping everything into one category. And yeah, usually you wouldn't do 50-50, you might make it more like 80-20, but basically the whole point is that you're balancing the data set more, so that way your machine learning model isn't making these like assumptions off the bat. And yeah, that's like one thing is be super careful with when you're training your model, because you don't know why your model's making the decisions it is. So a lot of your like analysis should be kind of figuring out why it's kind of making those things sometimes. If you're working with these types of models, because like, you want to make sure that your accuracy is actually accurate. So yeah, in this case, accuracy is measured by true positives and true negatives over the total predictions. So that's a pretty good metric of seeing out of your total predictions, how many of these are actually true positives and true negatives. And we also have something called precision. And precision is basically like seeing how precise, I guess, your data is. But basically it's looking at out of your true positives, how many of these are, like out of your true positives and false positives, how many of these are true positives, and you want a high percentage for that as well. And yeah, mean squared error is very important for regression. Basically, this is just looking at how much error you have in your model, and you want to have as low of a mean squared error as possible. So yeah, that's my, I think that's my final slide, yeah. Are there any questions so far? Yes?
Okay, so when the machine is deciding if yes, it has leaves, or yes, or no, it doesn't, how exactly does it, what is it analyzing specifically? Like, because you said there's different things it can look at, like smoothness, etc., off of what we want it to identify. What exactly is it doing to identify?
So I think one example would be like if we put it in our data set. Let me try to go back. Okay. So if we put our data set in like this, it could use like those zeros and ones and then say like, hey, if it has ones in these areas, it's like more likely to be this object and more likely to not be this object. So it can use like those numbers. And like with linear regression, for example, linear regression is just like linear, it's like a line. So it like plots like a line relationship between the two objects, and then using those points, it'll maybe try and like make an equation to make a line to see if it can like chart that. But there's also different types of machine learning models. Like there's image recognition, which you could also do. So if we had like an image recognition machine learning model, it could look at, like the model would analyze, okay, is this tree smooth first of all, or like is this tree, or is this object smooth, or is this object tall? And based on its predictions for all of those things, it would make a prediction on whether it's a tree or a bike. So it depends on the model.
Okay.
Yeah. Yes.
Just to make sure I'm understanding correctly, if you had an SVM with say n classes, then would that mean you have n support vectors?
Yeah, so I think, wait, what are you saying for n?
Like in this case, you're distinguishing between two classes. So does that mean you end up with two support vectors?
Oh, okay. Yeah, so support vectors are basically, they're charted from the closest points to the line. So it's not dependent on like in this case, like let's say you have two classes, it's not always that you'll have like just two vectors, but it's looking at the points that are the closest to like that dashed line. So like let's say like one side of the line had like 3 points, and then one side of the line had 2 points that are like the closest to it. It'll use those 3 points that are the closest to like chart that support vector. and then it'll like use the 2 points big on the other side to chart that support vector. So yeah, I don't know, do you have a better answer for this?
Well, I think support vector machines are just like a hyperplane that separates like 2 classes. So like with 3 classes, you probably want to use something like not this.
Yeah. So like the main part of a support vector machine is just like that hyperplane, which is that black line. But the vector is what like determines the slope of that line, and then to determine the slope of the line, you're just using those closest points. So it's just looking at that. Yeah.
So to follow up, how do you know how many points you want to use as like those number of closest points, or as the support vectors?
So sorry, can you repeat, like, is your question like how do you like decide which points to look for like the support vectors?
Yeah, basically, how do you determine what's your support vector?
Yeah, you basically look at the points that are like closest to your hyperplane. So you can just do some like normal calculation. Right, so like distance from the plane. There's a formula for that. I don't really know it right off the top of my head, but.
Okay. Also, our rating will go like into the details of it, but I'll answer your question also individually, I think, later, and have more detail. Then yeah.
So I think Eric just mentioned that like, it's like this is split like between 2 classes, but if you had like between 3, wouldn't it just be like a plane? Because that's like, so like in what case is like your hyperplane a plane instead of
Oh yeah, that's a great question. It's more about like the dimensions of your points rather than like the number of classes, because like I think you can only separate 2 classes of a support vector machine.
Okay.
Yeah, so that's why like if you have like a 4D thing, then you would have a 3D separation, and that kind of impacts it. But, yeah. Any other questions? Yeah. Okay, let me. Yeah, so a hyperplane basically is the thing in the SVM that supports the 2 classes, or like separates the 2 classes. So the hyperplane is what we use to kind of classify our model into, like in this case, if we're looking at the bike or the tree, we would chart that hyperplane in between our points, and our model would do that for us. And then based on whether those points lie like below or above in the like 2D example, it charts it into whether it's a bike or it's a plane. So it's just like separating your predictions into its different like groups, and then that's how it like classifies the points.
So it's like the line of separation.
It's a line of separation, yeah. But then in some cases, like it's a line of separation here because it's 2D, but if it's like 3D, then it might be like a plane of separation, and then that's how it kind of builds up in dimensionality.
If we were to look at this 2D example, what if you had points that like were kind of mixing together? How would you create a line of separation?
So if you had points that were like mixing together, or are you saying like if they're close to each other?
Like what if they're like kind of overlapping?
Okay, yeah, like if you had a lot of points overlapping, then basically it would kind of come down to like how close it is to the line. But that is like the case where like if you had like a line here and if you had a bunch of points that are basically on the line, your model's predictions will be less accurate because it's based on like the super tiny differences that are kind of separating it into like being a bike or being a tree. So that's why for SVMs we want to have a lot of distance in between like our line and the points, because like the more distance you have in between like your separation and like the points means that like it's a more accurate model. And then yeah, if there's like overlap in the 3D sense, then you wouldn't have a plane, you would have like a 3D object that's like separating the points. Yeah. Anyways, yeah.
Do the axis like x1 you got and x2, did they carry any value significance?
Are you talking about in this?
Yeah, and not graph.
Oh, okay. I don't think it like carries like a value difference. It's just mainly just to show the place where the points are plotted like on the graph itself. So it doesn't like I think we could switch this basically, and it doesn't really matter. Like we could have x2 on the bottom and x1 on top. It's just the points placement might switch, just depending on like what is being calculated in it.
Yeah, I'm talking about, is there like any difference if there was a point like on this side of x1 or that side of x1? Like.
Oh, yeah. There would be a difference in terms of how the machine learning model had used it, because it uses all those features to calculate where it's being charted on the graph. So like if it's more to the left, then maybe that's being influenced by something like height or something like that, and then maybe that's why it's more on the left. But in terms of classification, there's no difference, because if like our green point is like slightly higher or slightly lower, it's still going to be classified into its like classification, if that makes sense. So it's not going to impact like whether the model thinks it's a tree or like a bike in this example, unless it switches to being like on top of the line or being below the line, and then that's where it switches its placement. That's like the only case where it impacts the classification. Does that answer your question or?
At some point it will.
Okay, yeah. Yeah.
When it comes to the PCAs, they're applied onto the SVMs, right?
Yeah, it's principal component analysis is like a separate topic, but it's basically it's like applied onto the SVMs where you can apply to anything, but it's basically just reducing the dimensionality of your machine learning model. So SVMs are the model that you're applying onto your data set to classify your data, and principal component analysis is a step ahead of that where you're applying that onto your data set initially to reduce the variance in the first place.
So it deletes data sets from the table that you input onto the graph? Or
Yes.
does it delete graph points after you've already put in all of your data?
I think you could probably choose, but I think usually it is like after your data, you use principal component analysis first, and then you would use the SVMs because you want to like principal component analysis is like reducing the variation of your data set. So you want to put that like less variation, like that more condensed version of your data set into the model instead of putting in like this worse data set into your model and then kind of fixing it. So it's like you use principal component analysis first and then you put it into the SVM.
Okay, got it.
Yeah. Yes.
So for the last slide, is it like the quantity of the true positives plus true negatives over its forward prediction? So it's like, are there technically supposed to be like parentheses, or is it like?
Oh, yeah. There's so it's true positives plus true negatives parentheses over true.
And then
predictions.
same for precision.
Yeah, precision is true positives divided by true positives, false positives.
Okay.
Yeah,
And then
I'll put parentheses I think later. Yeah.
okay, and then for the technical project, are we expected to like all of the lecture material applies to the technical project, correct?
Yeah, and if you guys have any questions with the technical project, you can message your TA. And our CoLab notebook has instructions for you guys to walk through with the project, so it's not like we're just like giving you the code and like leaving you out to dry. It'll kind of like walk you through how to solve it. So yeah, and if any questions pop up, message your TA in your TA channel, and then that way like other kids can also learn from any mistakes you have. Yeah.
So one of the like techniques, if I'm correct me if I'm misunderstanding, is to like maximize the motion for the SVM is to add dimensions, right?
To maximize what?
To maximize the motion for the SVM is to add dimensions.
Yeah, more dimensions is like better in terms of accuracy, but it also makes your model less efficient because your model has to work with more dimensions. So because of that, it'll maybe like reduce your like runtime or something like that because it's taking so much time to work with those dimensions. So typically you do want to work with fewer dimensions if you can, and if it is accurate, because that means that your model isn't working through as much like runtime to get your results.
So that's why you do like PCA beforehand, right? So like reduce
Yeah.
dimensions and also get good data.
Yeah, so that's why you would do PCA or something like that beforehand, because typically you want to make your model do less work if possible. So that's like one big thing actually with data science is there's this thing called exploratory data analysis, or EDA, right? Yeah, exploratory data analysis, just making sure with Misha. But yeah, basically that's when you like clean your data set and you like filter it out and you kind of explore your data set beforehand before you put it into your model, because you want to make sure that you like have a good understanding of what data you're working with and clean it up wherever possible. So if you have like missing values in your data set, for example, you'd want to remove those values for your model. Yeah. Any other questions? Yes.
So I'm trying to visualize what it would look like if there are, like, I guess, 3 classes we're trying to separate. And you said we'd need to be in the 3-dimensional space to do that. And if we are in the 3-dimensional space, would we just use a plane? I don't really see how a plane would be able to do the job of separating 3 different classes.
Yeah, I'm trying to see if I can find like an image online or something.
Yeah. I'm so sorry, I know it's like...
No.
Yeah.
But yeah, I think, let me see. I think typically you will mostly work with it in a 2D space or 3D space, so usually you will just be working with like a line or a plane. But let me find a 3D thing. Actually, I'll look at this, oh, okay. Okay, I'll look at this later and I'll send you like a link that explains it better. Okay, if you have any questions that like I didn't fully answer, just message me after this lecture, and then that way I can like collect my thoughts and like type out a proper response. And yeah. Any other questions? Yeah.
Right, I think just related to that point, I think like for the vector machine, the support vector machine we're looking at, it's for 2 classes, so you only need 1 hyperplane.
Yeah.
But then when you have like 3 classes, then you need multiple classes.
Yeah. So yeah, typically you're working with just the line and the hyperplane in the 2D and 3D, but yeah. Okay. Any other questions? Yes.
I wonder if the what is the positive hyperplane and the negative hyperplane? Is it like all part of the hyperplane, or is it not just a plane?
Oh, it doesn't really matter if it's like positive or negative. It just matters like what side the point is, like relative to the hyperplane. So if the hyperplane is like a plane, for example, like let's say this is my phone, then it just matters like if my points are like on top of this area or like below this area. So positive, negative isn't like a huge thing. It's just like where the points are relative to the hyperplane.
Okay, so like in 2 dimension, the hyperplane is just a line, not a plane.
Yeah, in two dimension, it's just a line. Yeah, awesome. And then,
So with the number, so if you're like doing that table, that graph of like classification, would the number of dimensions equal the number of parameters? So like say over here, I know that has these has wheels. If you only have those two, it's only 2D. But then now that we have 7 parameters, would that be like a 7D graph?
so I mean, in this
no
case,
PCAs.
yeah, in this case, this would just be a 2-dimensional graph, just because we're only looking at bikes and trees, right? The other features are what kind of impact our machine learning model's prediction of whether it's a bike or it's a tree. But basically, what each point is representing is the prediction of what it thinks. So, like, if the point is like higher up, then it might be like, okay, there's like a 75% chance this is a tree, and 25% chance it's a bike. So that's why it's like at this point versus like over here might be like 33% chance bike, 43% chance tree, and like other percent chance, I don't know. So that's kind of like what impacts the points. It's just like how much it thinks it's like a bike or a tree. So in this case, it would be 2-dimensional.
Okay, so the parameters don't show up at all on the graph.
Yeah, the parameters just impact where the points are on the graph. So it impacts like the placement, but it doesn't actually impact like the dimensionality of the graph.
Okay, so like this, so it's just hidden behind a wall.
Yeah, the dimensionality is fully impacted by like the classification. So it just depends on like how many classification groups you're trying to put it into. Any other questions? Yes.
Wait, so then just to follow up, does that mean that each of the axes represent how confident you are in it being a specific class?
Yeah, yeah, so like each axis, the axis basically represents like, just like the overall graph, but then it's like the point placement on the graph that represents like, based on all the parameters where it thinks if it thinks it's like a tree or if it thinks it's a bike. And then the line is what separates it between the 2 classification groups. Okay, I might move on to the Kahoot.
Oh, first you're gonna do attendance.
Oh, attendance, yeah, I haven't lost it. This is a copy.
Is this week 1 or 2?
This
This will be week 1. I created another link for people who don't have Gmail addresses, or like the UW Gmail addresses, so you can access it using any Gmail address. But if you do have a UW Gmail address that works, please, we do prefer that. It makes it a lot easier to track. I put both the links either in the Discord or we will present them on the screen shortly.
Wait.
As QR codes. Yes.
Wait, the non-UW.
Week 1.
The non-UW email is has an extra space in front, so it leads to Google.
Oh, so sad. I will fix the QR.
Okay, cool. Just the non-UW one though. The UW one I think works. I'm sorry.
So here's the attendance link if everyone can take a picture of that real quick and fill it out just to say that you were here. And if you're having any trouble with like your UW email, I put a guide in the intro course resources, I think to say, or I think intro course channel, and you guys can indicate whether, or you guys can make your UW email work for a Google account.
Is this week 2?
This is week 1. Yeah. Our last week was week 0.
Can you make it so that we get like email confirmation back?
Oh yeah, I will.
Yeah, I think it's
Also,
cool.
let me quickly open the attendance page.
Yeah, I added it to your presentation.
What?
I added the attendance to
Yeah,
your
it looks-
presentation.
Oh, okay.
Yeah. Because they have both now.
Oh, okay.
The non-UW and the UW.
Wait one sec. Let me quickly open the attendance form and then.
Should be.
It's open.
Oh, it is.
I opened it.
Oh, awesome. And then, okay, I think everyone has it. Quick thing, Discord roles, make sure you guys have selected that. And yeah, okay. I also am gonna quickly I can actually see the screen properly. Oh yeah, feel free to go now. There is a Kahoot, so if you guys want to stay for that, you can feel free to do that. But Mission will leave the Kahoot. Oh. Actually, okay, I don't need it. Yeah. Okay. Well, I mean, they have to go, right?